Right now, as you're listening to this, there is an invisible, high-stakes game of cat and mouse happening right above our heads.
It's completely silent to us, yeah.
Exactly. You can't see it, you probably can't hear it, but the skies are just buzzing. We're talking about the exploding world of unmanned aerial
What
systems.
you and I would typically just call drones.
You're right, drones. And more importantly, the cutting-edge counter technology designed to stop them. So, the mission for today's deep dive is to figure out exactly how security forces detect and neutralize these rogue drones.
But the really fascinating part, the crux of it all, is how they manage to do this without accidentally snooping on your personal data in the process.
Because it's a massive technological tightrope.
Oh, yeah, absolutely. I mean, you have physical security demands on one side and then strict civil liberties on the other. And the entire balance hinges on some incredibly sophisticated engineering that most people don't even know exists.
Which is exactly why we're unpacking it today. We are pulling from a massive stack of research for this one. We've got legal analyses on signal interception, detailed technical specs from defense industry leaders like Drone Shield, plus some really eye-opening data on how drones are integrating into our everyday networks.
It's a lot of ground to cover.
It is. But before we jump into the deep end, I do want to take a quick second to thank the sponsors making this research possible. If you want to secure your own digital footprint while we talk about securing the airspace, you absolutely need to check out www.secureat.house and www.myprivacy.blog.
Great resources, highly recommend them.
Their support is what keeps us doing these deep dives. And speaking of support, it's great to have our resident expert here to help translate these complex defense concepts into plain English. Welcome.
Thrilled to be here. This is it's one of those topics that sounds like science fiction at first glance, but it is very much our current reality.
Yeah.
The sheer volume of what's happening in the airspace right now is just hard to wrap your head around.
Let's start right there, actually, with the scale of this, because what blew my mind in the research is that modern drones aren't just radio-controlled toys anymore.
No, not at all. They're essentially flying nodes on the Internet of Things.
Right. Just look at the IoT explosion. Back in 2015, we had about 15.4 billion connected devices globally.
Which was already a massive number.
But the estimate for 2025, it's over 75 billion. And drones are riding that exact same wave. They're leveraging 4G LTE, 5G cellular networks, and even low Earth orbit satellite constellations.
Like SpaceX's Starlink or Amazon's planned networks.
Exactly.
If we connect this to the bigger picture, you start to see why security agencies treat this as a nightmare scenario. I mean, if a drone is operating on a 5G network or bouncing a signal off a satellite, it can be controlled by someone sitting on the other side of the planet.
Wow.
So the traditional localized methods of stopping a threat, they simply don't apply anymore. And this introduces a fundamental problem in defense strategy known as the asymmetric threat.
Okay, let's unpack that concept for a second. What makes a drone an asymmetric threat, practically speaking?
Well, it boils down to basic economics and the sheer scale of the defense required. The cost to mitigate a drone threat is generally over 10 times more than the cost of the drone itself.
Over 10 times.
At least. Think about a bad actor buying a simple, off-the-shelf consumer quadcopter for maybe $1,000.
Right.
To defend against that single, relatively cheap device, a facility might have to deploy a multi-layered defense response that costs tens or even hundreds of thousands of dollars.
That's insane.
And it's an exponential curve, too. If a bad actor upgrades their drone just a tiny bit, say, by switching to a slightly better encrypted signal, the security team might have to spend a fortune on new tracking software just to catch up.
So you're trying to stop a cheap piece of plastic and circuitry with multi-million-dollar military-grade technology.
Precisely.
And the reason you, the listener, should care about this is that this isn't just happening in active war zones. The implications are entirely civilian right now.
Very much so.
We're talking about unauthorized payload deliveries. Like organized crime syndicates using drones to smuggle cell phones or contraband over prison walls. We're seeing intelligence gathering around critical infrastructure like power plants.
Or sometimes it's just a massive nuisance.
Yes. A single nuisance drone flown by a careless hobbyist can shut down a major commercial airport for days, which costs the economy millions of dollars.
Or it can force the evacuation of a crowded sports stadium during a major event.
Right. The threat vectors are entirely dynamic.
And the airspace doesn't differentiate between a teenager who lost control of their birthday present and a highly coordinated corporate espionage attempt.
That's a great point.
The defense system has to monitor the environment with the exact same level of scrutiny, regardless of the intent.
So if someone is flying a rogue drone toward a packed stadium, how do we actually see it? I imagine standard airport radar isn't going to pick up a plastic quadcopter flying below the tree line.
You're absolutely right. Standard radar would miss it entirely, or it would just confuse it with a flock of birds.
Because it's too small.
Exactly. Relying on a single sensor is a recipe for false alarms. So the industry standard to solve this is what we call a layered defense. You build an invisible net using 4 main pillars of detection, and they all feed data into a central command software.
Okay, let's unpack this layered defense because the engineering here is wild. What's the first pillar of this invisible net?
The first pillar is specialized radar. Now, unlike the massive spinning dishes you see at a local airport, these are compact, high-frequency systems designed specifically for small, fast-moving objects.
Okay.
They transmit radio waves and measure the reflections. That allows operators to identify airborne objects based on their specific size, speed, and movement patterns.
But even a specialized radar has to have blind spots, right? Especially if we're talking about urban environments.
It does. Radar struggles in environments with a lot of physical clutter. If you're in a dense urban cityscape with skyscrapers or a heavily wooded area, the radar waves just bounce off the buildings and trees, creating noise.
Which is where the second pillar steps in.
Right. Acoustic sensors?
So we're literally just listening to the sky.
Effectively, yes. These are highly sensitive microphone arrays programmed to identify the distinctive sound signatures of drone motors and propellers.
Because every drone model sounds a bit different.
Exactly. They all have a slightly different acoustic profile, so even if a drone is hiding behind a concrete building where the radar can't penetrate, the acoustic sensors might still pick up the hum of its rotors.
Which brings us to the third pillar, the visual element. Electro-optical and infrared sensors, or EOIR.
Right. Once the radar or the acoustic sensors detect a blip, they tell these highly advanced camera systems exactly where to look.
The cameras just snap to that location to visually confirm the threat.
Which happens more often than you'd think. But it's not just about weeding out a really large seagull from a quadcopter. That visual confirmation is often a strict legal or operational requirement before any security officer is allowed to press a button to neutralize the threat.
You have to have eyes on the target.
Always. But while cameras and radar are great, the fourth pillar is arguably the most complex and the most crucial for modern counter-drone systems: radio frequency, or RF, detection.
Here's where it gets really interesting, because RF detection isn't an active ping. It's not sending out a signal like radar does.
Oh, it's entirely passive.
It just sits there, scanning the environment for the radio signals that are used to control the drones, or the telemetry signals the drones use to send back live video feeds.
And finding that signal is like finding a needle in a haystack made of other needles.
Because there's so much noise.
The airspace over any modern city is already absolutely flooded with radio frequencies. Your cell phone, the local Wi-Fi networks, Bluetooth headphones, garage door openers, they all share the same spectrum.
So how does the system know it's looking at a drone and not my smartwatch?
It uses a technique called signal fingerprinting.
Signal fingerprinting.
Yes.
Yeah.
The counter-UAS systems measure the frequency, the signal strength, the bandwidth, and the specific modulation type to identify unique waveforms. And then they match these waveforms against a massive, constantly updated library of known drone signatures.
Oh, wow. So they're basically confirming that the specific shape and pattern of the radio wave belongs to a DJI drone or an Autel drone.
Right. Rather than someone's home Wi-Fi router broadcasting on the exact same 2.4 gigahertz band.
And it goes even further than just identifying the make and model of the drone, doesn't it?
Oh, absolutely. By using multiple antennas and some heavy-duty signal processing algorithms, these systems utilize direction finding and triangulation.
Meaning they can figure out the exact physical location and altitude of the drone in the sky. And here is the kicker. They can track the signal back to the person holding the controller on the ground.
That is a critical capability. Often, the safest way to mitigate a drone threat isn't to attack the drone itself, especially in a crowded area.
Right, because of falling debris.
Exactly. The safest route is to locate the pilot's coordinates and have local law enforcement intercept them directly.
But that brings us to the ultimate question, doesn't it? Are we trading our personal privacy for secure skies? If these defense systems are constantly sucking up radio frequencies, analyzing Wi-Fi bands, and pinpointing cellular signals to find a pilot, Are they reading my text messages?
That's the main concern.
Are they intercepting my group chats while they look for drones?
It is the single most important question to ask when we deploy military-grade technology in civilian spaces.
Before we figure out if the drone hunters are actually reading your texts, I want to quickly thank the folks who help us uncover exactly how our digital lives are being protected. If you want to secure your own home network and understand exactly where your data is going, head over to www.securiat.house and www.myprivacy.blog.
They really do offer phenomenal tools.
They do. Okay, so back to the big privacy question. Are these systems eavesdropping on us?
The short answer is no. The long answer is rooted heavily in federal law and some very specialized engineering safeguards. Looking at the legal breakdown, the use of these systems is heavily regulated by acts like the Electronic Communications Privacy Act, or ECPA,
Okay.
and something called the Pen Trap Statute, alongside FCC regulations.
Let's define that for a second, because pen trap sounds like something out of a spy novel. What does that actually govern?
Well, the term originally comes from old telephone technology pen registers and trap-and-trace devices.
Mm-hmm.
Today, it essentially governs the collection of routing information.
Routing information.
Right. Federal law strictly prohibits the intentional interception of the content of private electronic communications without a warrant. But you are allowed to look at the routing data, the origin, and the destination of a signal.
So it's like a piece of physical mail.
That is the perfect analogy. Security systems are legally allowed to look at the outside of the envelope to see where it's coming from and where it's going, but they are absolutely forbidden from tearing open the envelope to read the letter inside.
There's actually a quote from the research that serves as the perfect golden rule for this. It states, and I quote, "By focusing on how a signal is transmitted rather than what it says, these systems function as spectrum survey tools for security, not as eavesdropping devices."
Exactly. And the challenge for the engineers who build these systems is figuring out how to analyze a signal without accidentally looking at what's inside it.
Which brings us to the built-in safeguards.
Right. These systems are explicitly designed to only look at that envelope of the data.
So when the system kicks up a massive wave of RF data, what is the hardware actually doing to stay compliant?
It practices aggressive data minimization.
How?
When the receiver picks up a signal, the hardware and software immediately filter, truncate, or discard the data payload, the actual communication content, in real time.
In real time, so it doesn't even save it.
No, not at all. The system measures the shape of the radio wave to confirm it matches a drone's fingerprint, extracts the writing coordinates, and then dumps the rest of the data before it ever gets recorded or stored.
So they do not decode the text messages, the emails, or the phone calls.
Never. There is no long-term storage of communication content.
And from what I understand from the sources, this privacy-first approach extends to the visual sensors as well.
Yes, it does.
If those high-powered electro-optical cameras are scanning the horizon for a drone and inadvertently capture people walking down the street or cars in a parking lot, the software steps in. It incorporates privacy features that automatically blur or anonymize human faces and license plates when they aren't relevant to the actual airborne threat.
Which is a fantastic example of technology solving a problem created by technology. The system audits itself to ensure civil liberties are maintained while it secures the airspace.
Okay, let's play out our stadium scenario.
Right.
We have successfully detected the rogue drone. We used our custom radar, we listened to the acoustic signature, we matched the RF fingerprint without reading anyone's texts, and we visually confirmed it with a camera.
The full layered defense.
Right. But the pilot is ignoring all warnings. Now, for the action movie question. How do we actually take it down?
This brings us to the concept of proportional response. The mitigation strategy you choose depends entirely on the environment you're operating in.
Meaning you can't just blow it up.
No, you simply cannot shoot a drone out of the sky with a ballistic weapon if it's hovering over a crowded public stadium or a busy city intersection. The collateral damage from falling debris, the drone's lithium battery catching fire, or a missed shot, it would be catastrophic.
Right, which creates two distinct categories of mitigation: non-destructive and destructive. For domestic, civilian environments like those airports, prisons, and stadiums, security relies heavily on non-destructive mitigation.
Yes.
And the most common method mentioned in the sources is RF and GPS disruption, basically jamming the signal.
Right. When you jam the control signal, the drone loses its connection with the pilot. And most modern drones are programmed with a failsafe.
What happens then?
Well, when they lose connection, they'll either hover in place, slowly descend to the ground, or attempt to return to their launch point.
But there's another non-destructive method that's a bit more devious: GNSS spoofing. GNSS stands for Global Navigation Satellite System. It's the umbrella term for GPS and other satellite navigation networks. How does spoofing work?
Instead of just jamming the drone's navigation with loud radio noise, the defense system essentially lies to the drone.
It lies to it.
Yeah. It broadcasts a fake satellite signal that's slightly stronger than the real one. It tricks the drone into thinking it's somewhere else.
Oh, that is clever.
The security operator can slowly alter the fake coordinates, effectively taking control of the drone's flight path to steer away from the stadium and into a safe capture zone, like a digital Pied Piper.
I love that analogy, a digital Pied Piper. Or, if you want to get physical without causing an explosion, there are physical net launchers.
Yes, the net launchers are great.
These are devices sometimes mounted on larger security drones, literally designed to shoot a web over the rogue drone to tangle its rotors and bring it down via parachute.
It's very effective.
But if we shift environments, say, to a military base or border security in a modern warfare environment, the gloves come off. The rules of engagement change completely.
They do. In those theaters, and we see this heavily in the analysis of the current Ukraine conflict, you move to destructive mitigation. You don't care about a safe descent. You care about eliminating the threat immediately.
And the defense industry has developed some incredibly aggressive options for that.
Definitely. You have hunter drones, which are essentially fast, heavily armored interceptor drones designed to physically ram and smash into the rogue UAS midair.
You also have directed energy weapons.
Lasers.
Yeah, high-energy lasers that burn through the drone's casing. Or high-powered microwaves that instantly fry the drone's internal electronics, causing it to drop out of the sky like a stone.
And then you have the purely kinetic effects, physically destroying it with projectiles. The defense specs outline hardware like the EOS Slinger, which is an automated ballistic countermeasure system that tracks and shoots the drone.
And there are also these wild handheld devices like the drone gun.
Oh, the drone gun is fascinating.
It looks like a massive sci-fi rifle that a soldier holds, but instead of shooting bullets, it fires a highly directional beam of disruptive RF energy to sever the drone's connection instantly.
The overarching theme here seems to be that a counter-drone system must be entirely scalable and modular.
Right. The commander of a military outpost in a desert needs vastly different tools than the head of security for the Boston Marathon.
Exactly, but they both rely on that exact same foundational web of multi-sensor detection. That is the core takeaway here. The detection net is universal. The neutralization method is contextual.
So what does this all mean for you? As our cities become smarter and as our skies inevitably become more crowded with commercial delivery drones dropping off packages and flying IoT devices inspecting bridges, this counter technology is going to be integrated into the background of our lives.
It has to be.
This invisible, multi-layered, privacy-respecting shield is what will keep the airspace safe. It's the only way we can protect critical infrastructure, airports, and public events without inadvertently turning our cities into an invasive surveillance state.
It really is a remarkable achievement in engineering, finding that exact line between absolute physical security and absolute digital privacy and managing to walk it effectively.
It really is. And keeping our digital and physical lives secure is a theme we care deeply about here. So I want to give one final genuine thank you to our sponsors, www.securiat.house and www.myprivacy.blog, for supporting this deep dive and helping us bring this research directly to you. Check them out. They're doing great work.
Before we wrap up, I want to leave you with a final thought to mull over.
Let's hear it.
Throughout this entire discussion, we have focused heavily on detecting the radio frequencies and signals these drones emit. We look for the pilot's control signal or the video feed, but the defense industry is already tracking the rise of something called dark UAS.
Dark UAS.
Yes. These are drones programmed to operate entirely autonomously, using onboard AI and visual navigation. They do not emit any RF signals for control, and they do not broadcast video feeds back to a base. They just follow pre-programmed instructions in complete electronic silence.
Oh, wow.
So if the drones of the near future fly completely dark and silent, how will our privacy laws and our detection technologies adapt when there are no radio signals left to fingerprint?
Now, that is a terrifying and fascinating puzzle. We're going to have to rethink the entire invisible net. Definitely something to keep an eye on the sky for. Thanks for joining us on this deep dive, and we will catch you next time.